Hello everyone. So today we take a step back and we will mostly discuss about Lagrangian formalism and how symmetry, what is the consequence of symmetry in Lagrangian formalism. But before that, we will discuss a small a theorem in mathematics which is called Stoke's theorem, and it deals with integration of several variables. Okay. So let's say we are interested about integration of some multiple variable x mu. So for this lecture, mu can run from any number. It can run from any 1 to d. Okay. So let's say there are several variables. And let's say that we are interested in integration of some function. We are interested in integration of some function which is a function of all the variables. So this is a function of all the x mu's over some space over some d-dimensional space. Okay. So the d-dimensional space, let's say schematically looks something like this. We cannot draw a d-dimensional space, so we are doing it in 2 dimension. But let's say this is the range of space on which the x mu's takes value. Okay. So let's denote this space as M. Okay. So this integration is over M. So for example, so we consider an example. Let's say we are interested in 2 dimensional variables, and let's say we want to integrate over just as a region which is rectangular in shape. Okay, so this is x1 direction. So this is x1 direction which runs from A to B, and so this is the x1 direction, and this is x2 direction which runs from C to D, let's say. Then this symbol essentially means that we are integrating x1 from A to B, and we are integrating x2 from C to D. Okay, and then there we are giving some function of 2 variables. Okay, so this sign means. Now you see, in both these cases, the space on which we are integrating over, the space has a boundary. So the space has a boundary. Let me try to draw it in red. Okay, so this means M has a boundary. Now let's say we are interested in such cases, we are interested in a very special case where this function f can be written in this following way. So we are restricting to a special case where f is something like this. Okay, where epsilon mu is a d-dimensional vector, and dx mu is just del x mu. Okay, and if f takes this special form, then if f take this special form, then that case is usually the part of Stoke's theorem. Okay, and the theorem says that if you are given such a special f, so the theorem says that let's say you are interested in some ddx epsilon mu del mu x g. Okay, and it is over some range M. Then the question is that what happens on the right side, that's the Stokes theorem. So before we go into the right hand side, let's also discuss another point. So you see that whenever we have this region which has a boundary, then every point has a normal direction, right? And I am considering the outward normal, not the inward normal. So let's call it n. Okay, so this is n. So in our definition, so let's say here n as a function of x is outward normal to boundary of M. Okay. Then this theorem says that this is same as integrating over d minus 1 variables which are just restricted to the boundary of M. So usually the boundary of M is formally denoted like this. Boundary of M. Then you take the vector epsilon which was here and you take its dot product with the normal. And here you have just G. Okay. So this is the dot product of epsilon with outward normal. Okay, so you see that this is the powerfulness of this theorem. It says that here on the right hand side, on the left hand side, this is an integral over d variables. Okay, integration over d variables. Whereas this the right hand side, this is an integration over d minus 1 variables. Okay. So this is the Stokes theorem, and let's discuss some simple cases. So simple cases. The simplest case is when d equals to 1. Okay. So in that case, the left hand side is simply some dx which runs from a to b, and then you have some epsilon times del x of some, let's say, g. Then you already know the right hand side, because this is what we do all the time in definite integral of single variable. This will just become, so okay, so in this case then dx is just an interval. Then it has two boundaries. And you see that the outward normal at B is in this direction, and the outward normal along A is along this direction, right? Okay. and this quantity here, I write it as epsilon mu del mu, where epsilon mu is simply epsilon times x hat, so it's only in the positive direction. Okay, so that if you do this computation, you get back this thing. Then from the left hand side, what do we get? From the right hand side, what do we get? From the right hand side of Stokes theorem, we get that this quantity must be del m, I mean it must be evaluated at the boundary, epsilon dot the normal vector times g. In this case, the boundary is simply 2 points. So in this case, boundary is simply 2 points. A and B. At point A, epsilon dot n is minus epsilon. Why? Because the normal is on the opposite direction. At point B, epsilon dot n is plus epsilon. Okay. So with this input, then that above quantity just becomes epsilon times g of B minus g of A. So this is the exact result that we know from our lessons in definite integrals, but we just derived the same result in a more fancy way, and we will see the advantages later. So let's also now do a two-dimensional case. Okay. Actually, let's go back and let's do another one-dimensional case where we have a periodic variable theta, and the periodic variable, let's take value in this range. So theta is between 0 to 2 pi. Okay. Now let's say we are again interested in a computation of a of something of this form. As per our notation, we are using g of theta. Okay, such that the g of theta is same as g of theta plus 2 pi. Okay, unless this is true, the function is not globally defined. So this is another important condition, that the function g has to be globally defined. So let me write it here. This is a globally defined function. Okay. So if that is the case, then in this case again the thing will reduce to, so this is m, delta m, epsilon dot n, g. But in this case, you can see the region we are integrating over has no boundary. And as a result, this quantity is simply 0. Okay. Again, you know this because you know that when you try to integrate that total, for example, a very simple case. Let's say if you take g of theta to be exponential I n theta, where n is an integer. This n being integer is important. If n is not integer, then g of theta is not globally defined. That's why n has to be an integer. Then you can put this and you can explicitly check this formula whether it is correct or not. Okay, but this case just gives more. I mean this theorem proves it for more general more general functions. You don't have to prove it for order by order or case by case. Let's now do a two-dimensional example. So let's say now you have a two-dimensional example here, which we did already, which is x1 equal to a to x1 equal to b, and x2 equal to c to x2 equal to d. Okay, and let's say again, so again the point is that you see that the normal here is in this direction, outward normal is in this direction, whereas the outward normal on the other boundary, this boundary is on this direction. Similarly for the x2 variable. So let's say now we are interested in computation of a to b dx1, c to d dx2, some epsilon 1 del 1 plus epsilon 2 del 2 acting on some g, which is a function of x1 and x2. Okay. Then from Stoke's theorem, this will just become, from Stoke's theorem, it will just become 4 different pieces. Why? Because there are 4 different boundaries, 4 different boundary components. So this is one component, this is second component, this is third, and this is fourth. So you will see that this integration in this case breaks into 4 pieces. So what are the 4 pieces? So let's say you just first restrict to this boundary. So in this, along this boundary, x2 is fixed, right? Along this boundary, x2 is constant, and x1 changes value from a to b. So then you have a to b dx1. Then in this boundary, the normal is just minus x2 hat, right? That means the dot product, so in this boundary, the dot product epsilon dot n is simply minus epsilon 2. Okay, so that means that this will become minus epsilon 2 g of x1 and x2 restricted to c. So that's the first boundary component. Then second boundary component is, let's say, this one. So along this one, x2 changes from c to d. In this component, the normal is just x1 hat, x1 unit vector, which means that epsilon dot x1 hat is just epsilon 1. That means we get minus, it's not minus, plus epsilon 1 g of g and x1 now restricted to at b x2. Now we go to the third component, and you can convince yourself that this thing is just a to b dx1 plus epsilon 2. Why plus? Because in this case the normal is upward, so normal has changed the direction. Plus epsilon 2, then g of x1 and x2 now restricted to d. And there is a fourth piece where x2 goes from c to d. In this case, epsilon have a plus minus sign. Epsilon has a minus sign. G, now x1 restricted to a and x2. Okay, and this follows from Stoke's theorem. Stoke's theorem. Okay, so this is the theorem says that let's go back to the statement again. So let's say we are integrating over some n variables. Let's say let's say we are integrating over some d variables which takes value in some range m. Okay, and we are integrating a total derivative function. We are integrating a total derivative. Then the statement is that this thing maps to just restricting that, doing the integral over a d minus 1 variable, which you now integrate only over the boundary of that region. So you forget about most of the region and you just restrict to the boundary. And then what you integrate now the thing that was inside the derivative, which is g. On top of that, you have to add this extra factor, which is extremely important. And this extra factor is simply the dot product of the epsilon, the vector that appears on the left hand side, times a normal vector. So n was the normal vector. Okay. So this is Stoke's theorem. I would encourage you to do a few examples by yourself to understand this case. For example, you can check this case for some particular, so you can consider this case and consider some particular value of g, and you can do it. That for example, you can also do another case for let's say you are integrating over a disk. Okay, so let's say you are integrating something like let's say you are integrating over this. So then the integration is something like r dr d theta, and then you have some again epsilon mu del mu some g of r and theta. Okay, so again in this case you see that the boundary say last time r equal to r0 is the boundary. So then if this is the case, then this means that this integral, so this integral integrated over this range m is same as r0 d theta. Okay, d theta now takes value from 0 to 2 pi d theta epsilon theta g r0 theta. Okay, so this again this statement follows from Stoke's theorem. So you see that again the advantage. So this epsilon theta is the theta component of epsilon mu. So you again see the advantage that we had an integration of two variables and we have managed to reduce it to integration of a single variable. Okay. So when we will do later the calculus of variation, we will use this a lot, and this will become very important. Okay, so next time we will discuss Lagrangian and equation of motion from the Lagrangian.